Yeah, I'm gonna go like. Presentation will be on the screen or? All right, welcome back everyone. We're going to start our second session of this morning. I would like to first introduce the jury. We have with us Professor Pablo from the University of Victoria. Giacomo Franco. We have Professor Estelle Blanco from the University of the West Country, Professor Gauthier Chat from the University of Paris-Occidentale, and myself also from the University of West Country. So, as you know, you have 15 minutes to present, 15-minute discussion will follow. Yes. When you get to the 30-minute mark, I will wave, try to get your attention so that you can wrap up. If you ever see me standing up, it's because you're close to over time.
Yes,
and it's time to finish. Okay. But don't worry, that's what happens. So, welcome everybody here with us, welcome everybody online. I remind you, you can also make comments and ask questions in the chat if we have time to go. Pal, the floor is yours.
Thank you. Hello everyone, I'm Pal, and today I am presenting an integrative species distribution model for an ecosystemic-based management of marine protected areas. So in the last couple of years, we've made a lot of progress in establishing more and more marine protected areas, or MPAs, around the globe. Many of these in the framework of the 30 by 30 initiative, which is to place 30% of all habitats around the world under protection by the year 2030. Now, the problem with this approach is that there is no evidence that just simply increasing the sheer area under protection actually protects ecosystems. And the reason for this is that many of these MPAs are just terribly inefficient. Many of them are what are called paper parks, so they only exist on paper. They don't provide any actual protection. And there are a number of reasons for this, but one of them is that many MPAs are very poorly placed for a number of complex reasons. One is that we just don't have really good data for most species as regards to their precise distribution around the globe. So we don't know for many species where their most vulnerable habitats are that must be protected with priority, because conducting the comprehensive surveys of species distribution is very expensive, time-consuming, and difficult. But we don't have to do it because there is a more efficient way, which is a species distribution model, or SDM. Now, to construct an SDM, you need two kinds of data. You need, first, a list of sites where the species is confirmed to occur, and you need environmental variable layers. And to construct an SDM, you sample these environmental variables, sample their values at the occurrence sites, and you use this information to construct an SDM, which is a mathematical model that describes the relationship between the likelihood that a species will occur at a particular place and the environmental values prevailing in that place. Now, what makes this so powerful is that you can then take areas where there is no occurrence data known, apply the SDM there to the environmental variables there, and predict if the species is likely to occur there. And therefore, you can model the distribution of species over large areas with relatively little effort. And it doesn't even stop there. You can then combine and integrate species distribution models for multiple species together in the same area and identify sites that overlap in their distribution, which are key areas that support multiple important species. And placing protected areas here might be way more efficient for the resources that are expended into the maintenance of the MPA. So this was my aim, to construct such an integrative species distribution model for a marine protected area. And I did it here in northwestern Spain, you can see, in the autonomous community of Galicia. And in this community, there is a maritime national park that includes the islands of Ons, Salvador, and Cortegada, and particularly for my study area here, the CS Islands at the very south. So this is my study area. Now, the CS Islands is a protected area already. It is part of a national park, part of the Natura 2000 network. But it is not very strictly restricted, and there is quite a number of human impacts that are relevant here. There's beach tourism, for example, and most importantly, there is a very productive and quite large artisanal fishing fleet operating within the confines of the MPA. So my goal here was to identify areas that are the most important for the ecosystem of this area, and to identify which one of these should be prioritized for stricter conservation, for example, by establishing no-take zones within the MPA. So to do this, I needed a number of species, and I chose three species. Two of them are very important fishery resources, and the first of these is the common cuttlefish, which in the park is fished using trammel nets, and it is one of the more economically significant species in Galicia. But despite its importance, there has currently been no SDM constructed for it in this study site before. The second of our species is the common octopus. It is the fourth most important fishery resource in the entire autonomous community, and in specifically the Thesis Islands, octopus spot fishing is one of the most common fishing strategies that are used by artisanal fishers. And the species distribution model for this species was constructed last year, actually by an IMBRC student. My third species is the greater pikefish, which is not a fishery resource. It is, however, a potential conservation flagship species. It is quite large, up to 50 centimeters long. It looks very unusual, and there are already some tourism companies at the Thesis Islands that organize snorkeling trips for tourists just to see this animal. And the SDM for this species was constructed in 2021. So, I have now these three target species, and two of them already have distribution predictions based on SDMs. You can see them here. And you will immediately notice that these two species have very, very similar looking distribution predictions. So they have a very large overlap in predicted distribution, and possibly the cuttlefish will have a similarly overlapping distribution. And maybe then, if I construct an SDM, we can use this to identify overlapping areas. So to do this, to construct the SDM for the common cuttlefish, again, I needed two kinds of data. And first, the occurrence data came from Project Cefa Parques, which was conducted by the Marine Research Institute in Vigo. And this comprised visual census dives carried out in transects. And a total of 114 dives were carried out. And out of these, at 44 sites, there were confirmed sightings of cuttlefish. Second, the environmental variable layers came from the database of the national park and from Project Strauss, which was also a monitoring project carried out by the Vigo Marine Research Institute. And I used a total of 8 environmental variables, and these were depth, distance from the coast, slope, standard deviation of the slope, which is a measure of the roughness of the terrain, wave exposure, and here you can see very clearly that there is a more exposed and a more sheltered coastline to the island. Then, bottom temperature, and this is a seasonal variable, so this was subdivided into bottom temperature in the spawning season from February to October, and in the non-spawning season in the rest of the year. And similarly, bottom salinity, which was similarly subdivided by season, spawning and non-spawning season. And finally, substrate type, which is very diverse around the islands, but for our purposes, it is a binary. It is either a hard rocky surface or a soft sandy surface. Now, I had this huge stack of variables. How do I actually choose which ones are relevant for the model, which ones actually describe a relationship with the occurrence of cuttlefish? So I used an ensemble modeling approach, which constructs a number of different models and averages together their results. And the first model in the ensemble that I used was a generalized additive model, or GAM. This is a very common first step for constructing ensemble models. To select the correct model, I used an automatic stepwise model selection process, which takes a base model, adds or removes a variable, compares the two models for performance, gives the better one, and then repeats this step until it cannot improve on the model anymore. Now, at the end of this model selection process, I selected the 5 best performing models that were selected by this process, which performed essentially equally well, and based on the principle of parsimony, I chose the simplest of these final models to be my final model. And this finished GAM model included 5 variables, which were slope, standard deviation of slope, substrate type, bottom temperature, and wave exposure. And there was also an interaction term between the substrate type and the seasonal dimension of the bottom temperature. And here we have the distribution predictions made by this first model and the preference for the spawning and non-spawning season. And the preferential habitat that is described by this model has a low slope, it has relatively rough terrain, sheltered from the waves, and has a slight preference for higher temperatures. And next, I integrated these two seasonal predictions together into a yearly average with a weighted average, where the weight was the length of each season in months. And here we have our first prediction of cuttlefish distribution by our first model. Now, my second model was a maximum entropy or maxent model, which used the same variables as the GAM model for comparability. This is standard practice when constructing ensemble models. And the preferential habitat that is described by the maxent model is very similar to that described by the GAM, but the actual distribution predictions made are somewhat different. You can see that it has a lower seasonal variability. It is more restricted in extent. And there are these four very specific, very small, localized, very high likelihood occurrence points on the roughest areas, the rough terrain areas on the sheltered eastern coastline. And the yearly average of this model looks like this. Then my third and final model was random forest, which is a really quite sophisticated model. It uses randomly restricted decision trees to make predictions. And unfortunately, it didn't work. The model predicted that in the spawning season, cuttlefish would prefer soft bottoms. In the non-spawning season, they would prefer hard bottoms. And this goes completely opposite to every literature about the spawning behavior of cuttlefish, which essentially agree that they anchor their egg cases on harder bottoms in the spawning season. And the source of this error was likely an error in the generation of pseudo absence points for this model, which is a prerequisite for constructing this kind of model. And due to time constraints, this model eventually had to be dropped from the construction of the ensemble model. So, in the end, I had two completed predictions from two different models for the distribution of cuttlefish. And to construct my ensemble model, I used another weighted average, and the weights here were the area under the curve, or AUC values, of these models, which are a performance indicator. The higher the AUC, the better the model performs. And based on this average, we can see here we have our final distribution model for the cuttlefish. And this distribution model reproduces very neatly those same four high likelihood occurrence areas on the eastern coast. So we come back to our original three species, and I have now completed the distribution model for the cuttlefish. You can see here. And you can immediately notice that it does indeed have a somewhat similar distribution to my other two target species. So we can now integrate the three together and see where they overlap. So first we look at where there is a high likelihood of at least one of our species occurring, and the entire eastern coast just lights up. This entire area is for at least one of our target species in every location. There is a high likelihood of occurrence. But we can also look at it in a more strict way and look at where the three species are likely to co-occur together at the same time. And again, it is those same 4 points, here, 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 and here. So we can say that these 4 points are not only ideal for the cuttlefish, but these are ideal for all three of our target species, and they are likely biodiversity spots that support even more important species. So we now have our integrated model. How do we make conservation decisions based on this result? This map is not very good for visualizing our results in this term of identifying the extent of these important areas. So let's look at it like this instead, with thresholds. And pay attention to these 4 red areas, which all have at least 90% chance of at least one species occurring. And at the core of each of these red areas, there is one of those small co-occurrence spots, which is important for all 3 of our species. And based on this, we can say that there is 4 distinct areas which can be identified, which might be prioritized for stricter conservation because they support multiple important species around the islands. Now, if this was it, I would just say, well, then let's put all 4 under a no-take regime, but that's not that simple because there are people here. There is, again, quite a lot of stakeholder use for these islands. And based on we have to make socio-ecological considerations to prioritize between these areas. And based on these, I suggest that this area here, Vinos Island, should be prioritized for conservation. This, based on the environmental characteristics, this is an ideal fishing spot. There is like a lot of fishing pressure here, but there is no beach here. There is therefore no beach tourism. And therefore there is both an impact that must be protected from, high fishing, and because there is only one significant stakeholder operating there instead of 2, there is more likelihood of a successful stakeholder dialogue where instead of two stakeholder groups possibly pushing back in concert against a conservation initiative. So, my work therefore identified these important co-occurrence areas at the MPA, and I have made some suggestions based on socio-ecological considerations for which areas to prioritize for stricter conservation. However, there is clearly a number of ways in which this work can be improved. One of these could be to construct a climate model for the Thesis Islands, which could be used to construct future distribution predictions with SDMs, and see how, in the future, with the changing environmental characteristics, with climate change, where the distributions of these species might be shifting. And therefore, we might cover these also with conservation efforts and essentially future-proof our conservation regime. Another issue is that we do not have a really good data on how different stakeholder groups use this area. So, for example, we do not know where exactly the most fishing occurs, and this would be important to identify which areas are actually under the highest threat. Unfortunately, this data at this time is not available. And finally, this is a very local effort that I had, but the framework under which I made it can be used in global contexts in various locations, and particularly the approach of strategically choosing species to be included in an integrative SDM could be used to immediately design MPAs for efficiency right from the start. By choosing, for example, you choose an iconic species for outreach, you would choose a commercially or culturally important species to win support from local communities. And this way, by choosing what species to study, you can immediately affect the outcomes of your planning effort. Thank you very much for your attention.
You were like 15 seconds over time, so nothing to worry about. So I will turn to members of the group. If you want to start with the discussion. Don't fight, please.
Okay, congratulations.
Thank you.
It was a very clear presentation and easy to follow, so thank you for that. And well, just two publicities, for example. That prediction that you made for the categories, will you prove in situ if it's true or?
Sorry?
Will you prove in situ if that predictions?
It is actually already being proven in a way, because the Vigo Marine Research Institute, where my main supervisor, Jorge Hernandez Ucera, is working, is currently applying for grants for a project called EcoSet, which would study the behavior and distribution of cuttlefish further at the CS Islands, because the latest data, as you might have seen, is from 2015. It is over 10 years old, and they're currently applying for more to conduct a follow-up. And an interesting aspect of this is that the study area has been shrunk essentially to the distribution that I have predicted. Based on my model, Dr. Hernandez has made this decision, and therefore we might see that in this follow-up project we might have possibly a higher proportion of occurrences in these areas. And also, this project is not only concerned with distribution, like the Cephas Parques project. It also is concerned with behavior and seasonal, yes. And possibly, this means that this model might already be doing some work, increasing the efficiency of research and conservation efforts, because with such a project there is a limited amount of resources, and if you concentrate the sampling efforts to the areas where they are most likely to be found, you might have better results.
And this, which software have you used to do maps?
With software? QGIS?
Congratulations and
Thank you. Thank you.
It was almost the same question to the map validation, the model.
Yes. Yes. Yes.
So, did you run any validation process when you're using historical data or something like this?
I have used a validation process for the models by setting aside a part of my occurrence data In the case of Maxent, I believe it was 20% of my sampling points, and in the case of random forest, it was 30% to validate the results. And these results indicated that my models were accurate. I have not planned any validation process in situ.
Yeah, thank you, Paul. I really enjoyed your presentation.
Thank you.
It was visually aesthetic and very pleasant to follow. Also, thanks to your flow and logical organization. So I have several questions. The first one is about the relevance of using the species distribution models at this spatial scale, considering that you're talking about species that are highly mobile.
Yes.
Did you have any thoughts?
These species are indeed highly mobile, especially the cuttlefish, and they are actually known to migrate out of the partially out of this study area outside of the spawning season, because this is for both the cuttlefish and the octopus. This area is a spawning point, so it is a brooding area, and because of this, despite the fact that these species are highly mobile, they would periodically return to this area, and therefore they reproduce here. So, despite the fact that in part of the year they might not be found here, there is still high value in identifying where they are using, when they are present, these areas, which might be protected.
Do you know if those species display different behavior or movement patterns between day and night?
I have not studied this for this project. I do not know.
It is possible. I don't think they migrate very far away, but...
It is possible, but also the resolution of my data did not allow this to be studied, because my data, at least the occurrence data, comes from scuba diving. And this would mostly only be done during the day. Yes, it is true, but unfortunately this was outside of my control. This is clearly a bias in my data, which could be rectified in the future with a different project, possibly with the use of automated censuses that do not involve human divers. This is a possible improvement, yes.
Talking about bias, what would you, if you were given the opportunity to limit some other bias, have you identified some other bias?
There is a bias that I have identified, which is the wave exposure. So if you go back to my environmental variables, you will notice that, and I think I have said this, that the coastlines of the islands are very asymmetric in terms of wave exposure. And this is because the island is located in the mouth of the Rio de Vigo. It is a bay that faces out into the open ocean. And because of this, the eastern coast, which is facing the continent, is very sheltered. And the western coast is very, very exposed. And this did, in fact, influence where dives took place. Originally, the sampling plan involved subdividing the area into cells and randomly performing 4 dives in each of them. But due to sea state conditions, it was often not possible to perform dives along the western coastline. You can see this on the map, that there is much more dives on the eastern coastline than on the west. So this is a possible source of bias.
We had a connection that is exactly the one I was thinking about. You tell me what all the time. No, you're yeah, you know, I have no experience in modeling, especially species distribution models. I'm more like an old-fashioned didactic taxonomist, go to the field and collect samples. And if you ask me about this distribution of Segnatus acus octopus and Sepia vulgaris, the first thing I will tell you is that you will find them in spreadlets.
Yes.
I was surprised to see that in your habitats characterization, the vegetation covering the substrate was not considered.
This is because this data was not available. I wanted to include it. The problem with this area in terms of data availability, it is in a very well-covered area of the world. It is on the coast of Spain, but it is a very small area. And because of this, there are many global data layers which simply do not have a high enough resolution to cover this area in any reasonable detail. For example, Copernicus data, the resolution of Copernicus data only covers 4 or 5 cells of this area. And unfortunately, I have considered this because I have also encountered this in literature, that particularly, for example, pipefish very much are linked to seagrass beds, but I was not able to find any sort of data on the description.
There's a national park, a small national park, and they don't have an habitat map.
I have not found it. I have not found it. I have found the sampling process did record the conditions on the bottom, which did include if there was seagrass, but this was only available for the sampling points and not for the entire area, and therefore I was not able to use it to make predictions.
That should be your first priority, in my opinion. Maybe the last question. So you identify 4 different areas.
Yes.
That might be interesting, and I like your idea to say, okay, in most of them I have 2 activities, so instead of dealing with 2 angry people, 2 angry categories of people, I will
only 1 angry category of persons,
to
yes.
the one where there's only 1 category of people, then easier to deal. Can't you see other criteria on which you can base your thinking to choose among those 4 areas?
Sorry?
Yeah, except of us making as few people angry as possible. And what other criteria?
The other important criteria was the prevalence of high human impact in the area. So these were the 2, like how impacted the area is by human activity and how likely it is that the dialogue here will be successful. And because of this, out of the 4 areas, one of them, which is the one I chose, is sort of like a middle ground in this term, which is it is impacted, but is not. Okay, I have so many animations. Okay, here. So this area here is completely undeveloped in the Southern Cape. There is only a lighthouse here. As far as I know, beyond some hiking routes, there is no human activity in this area. This and this area, these are beaches. So there is a high human impact, but both tourism and fishing is present here. This is a rocky coast, and I know from people who were involved in the Cephas Parkes project, they informed me about this, that this is a very popular fishing spot. So there is a high impact.
Fishing from the coast?
No, artisanal fishing. Recreational fishing in the islands is not allowed. Only artisanal fishing by local registered fishermen in the autonomous community is permitted in the area.
I was more thinking about the ecological functionality of this zone, because you base your evaluation on presence or absence, but
Yes.
the presence of the species doesn't mean that the area is especially important functionally. So yeah, I don't know how you could solve this and try.
Yeah.
You
Well,
try to assess the functionality of each one of these zones.
Well, based on just presence absence data, I do not believe that this is possible. But for example, this is why I'm very excited about this EcoSet project that I mentioned before, which will in fact assess more about the structure of the population of cuttlefish in these areas, and maybe this would allow more detailed assessments of functionality of these different habitats. These suggestions made are very preliminary because the area that I did my work in has a very poor data in many of the relevant forms of information that are necessary to make these decisions.
Okay, thank you again.
Yeah, I'm going to ask you presentation, sure. I would have questions, but I'm not going to ask them because we don't have time. But I would insist, I would also insist on the quality of the presentation. You managed to explain complex methodological approach in a to me, very simple and very engaging manner. And you didn't stick only to your statistical results, which are complex. You used those to actually do ecology and do inform public policy and things like that. So very congratulations.
Thank you very much. Thank you.
Up next.
Up next is Manager.
Making his announcement.
Always. Just, it's just
Okay. Okay. Thank you.
whenever you're ready.
Okay,
15 minutes for the
Okay. Good morning, guys. My name is Manja Pramod, and I'm going to present my thesis topic, Diversity of Deep Sea Vertical Wall Communities in the Galapagos Archipelago. And my work was hosted at the National Oceanographic Center, Southampton, United Kingdom. So first, let's look at why it is important to study these vertical wall communities in the Galapagos Archipelago. You may have known that Galapagos is known for its high endemism, even though these pristine habitats are poorly understood and largely overlooked. So it is imperative to identify the potential links to these deep sea habitats, which are still unknown. Also, there's an urge to define the first baseline of these pristine habitats before the climate change changes these habitats, before we document their initial characterization. Also, it is imperative to understand what variables shape the community structure of these Galapagos vertical wall communities in order to develop effective conservation strategies. So I have three main objectives. Primary objective is to characterize the epibenthic megafaunal community diversity within these vertical wall sections. And the second objective is to examine which primary abiotic factors, specifically site, depth, and substrate, and how these variables shape the community structure. And lastly, to assess the presence of vulnerable marine ecosystem indicator species within these vertical wall sections. So data gathered for this study were collected by RV Falcon 2 expedition that happened on 2023. And within this expedition, they had deployed a ROV called SU Bastian, and the red star is denoted the sites that this ROV was deployed. And this ROV deployed in collected high-resolution videographic data in three depth categories: 400 meters, 550 meters, and 700 meters. So this is the summary of analysis I used. Initially, ROV video transect were used to extract image frames, and those image frames were uploaded to online annotation platform called Beagle 2.0. And then those images were manually annotated. And within this study, I have annotated roughly around 13,500 annotations. And then complete taxonomic checklists were created from the annotations. And I also used descriptive statistics to have an understanding about the broad scale community structure, then followed by univariate statistics, especially beta diversity and alpha diversity. For multivariate statistics, I used NMDS analysis, hierarchical cluster analysis, followed by Permanova and simple analysis. And finally, BME indicator species were identified based on the guidelines provided by FAO 2009 and ICES 2020. So this is a snapshot of a vertical wall community from the San Cristobal site. And as you can see in the middle, there's a square-shaped quadrate denoted by the red arrowhead. So this quadrate was placed in each and every image frame in the same exact position. And within this quadrate, all the morphospecies were annotated. And as you can see, highlighted from the blue arrow, sometimes these species will span outside of the quadrate. So in these occasions, even though they are spanning outside, the whole organism were annotated just because otherwise it will be unable to identify them to the lowest possible taxonomic level. Also for this study, I used an open nomenclature system proposed by Horton et al. In 2021. So for example, I used certain terminologies like closely familiar, has an affinity, or identical. So now let's look at the community structure of the epibenthic megafauna in this Galapagos vertical wall sections. So in this study, I recorded 123 morphospecies, which is remarkable, and they spanned across 7 major phyla. And the highest number of morphospecies were recorded from the phylum Cnidaria with 55 morphospecies, followed by phylum Echinodermata with 23 morphospecies, and Arthropoda with 17. When you go to the Order and class level, Order Decapoda had the highest number of morphospecies with 17. So for descriptive statistics, I used class and order species diversities plotted against depth, each individual depth transects. And from here, you can see that there's not much depth or size specificity even though some texts are like Corallimpharia, Gnoidia, Holothroidia, they showed a certain level of site specificity. Also for alpha diversity component, I investigated on species richness, Shannon diversity, simpler diversity, and I also plotted total cumulative species richness against all depth transects. So here the most important figure is figure A, which highlights the rarefaction curves of species richness, and you can see all the confidence intervals were highly overlapping. So it suggests that the observed true diversity here is not statistically significant. And figure D is also important because it highlights that the prediction of total morphospecies, and I recorded 123. It suggests that I have almost recorded, like almost all the morphospecies have been recorded in my study, and which is remarkable because like image-based analysis are known to undermine the actual species diversity, but here I think I have done a great job here. So I also investigated on the terminal slope values of the rarefaction curves, and the first graph suggests that all my observed terminal slopes are well below the baseline value, which is 0.02 species per individual. So in a simple term, this says that if I annotated 50 more individuals, I will only increase my morphospecies count by just 1. That's the baseline. So my values are way lower. So this suggests that I have like found out almost all the morphospecies within these vertical wall habitats. And also I calculated the sample completeness estimates for each site, and remarkably my values were really high, like 99% and 98%. So it suggests that I have covered almost all the morphospecies that are present in this study area. Here I also investigated on the beta diversity, especially Sorensen beta diversity partitioning, and this is like a busy slide, but the take-home message from this slide is that I observed turnover component is the dominant factor compared to the nestedness component. In simpler terms, this says that within site and within depth comparison, species present are like this species structure is defined by species replacement rather than having a subset of same species throughout the transects. And interestingly, when I look at the turnover component across similar depth, I recorded really relatively low values compared to the cross-site comparisons. It also suggests that a partial depth structuring within these vertical wall habitats. So now the bigger question is, are there any site depth or substratum zonation within these vertical wall sections? So in order to investigate this, I did the hierarchical cluster analysis using a Bird's D2 methodology combined with Bray-Curtis analysis, and I identified 8 ecologically significant clusters, and all the cluster separation were statistically significant according to the Permanova analysis. And I also conducted a simple analysis just to figure out which species contribute to the dissimilarity between these clusters. And interestingly, this analysis showed that certain dominant species are disproportionately creating the dissimilarity rather than few number of rare species. Also, I aligned site depth, substratum, and coral presence and absence of coral rubble underneath the hierarchical clustering, and you can see certain clusters like cluster 1, cluster 3, and cluster 6. They have a site and depth specific structuring, even though other clusters had like a mixed components of different sites and different depths. That being said, certain taxa exhibited site, depth, and subset specificity. For example, like Actinocephalias aurelia in the first picture were recorded in extremely high densities at San Cristobal site, around 400 meters. And like species like Madrefora acuulata were only confined to depths around 400 meters and 550 meters, which indicate a depth specificity. And this observation was also observed by Salinas de Leon et al. In 2020 in the Galapagos region. And some species like Munida species or Ophiophorus acuulata were observed to have extremely high species aggregates that can be attributed to their subset characteristics, such as the presence of dead coral rubble network or presence of crevices within the larval rock formations. Also, I observed the presence of keystone structures within these vertical wall sections. So, keystone structures are those structures of geomorphologically or biotic components which known to increase the microhabitat or provide niche partitioning. Also, these keystone habitats are known to have favorable hydrodynamics and enhance food availability for species that is within this species aggregates. So this is an interesting finding within these vertical wall habitats. Also now let's look at the presence of vulnerable marine ecosystem indicator species. In this study, I recorded 32 vulnerable marine ecosystem species, which is remarkable, and I also plotted their densities. And when I compare the transect-wise presence of VME indicator species, almost all the transects recorded more than 50% of VME species densities, and some transects were reaching high numbers around 95% or 94%, which is remarkable. And the next question is, so what drives the community structure in this Galapagos vertical wall habitats? So from my data, I observed that site depth and substratum are interrelated, and they are acting as confounding variables. And it's also from the hierarchy class analysis, it was evident that similar assemblages occurring across different clusters, suggesting that there is like complex multi-level interactions, including some unexplained variability, which can likely be explained by other environmental or biological factors that I haven't investigated. So in this study, it's also revealed that subset-specific characterizations such as surface to area ratio or surface to viscosity index or slope might be better explaining this unexplained variability in this study, in this data set. So what's the importance of these findings? First, I observed all three vulnerable marine ecosystem habitats as defined by ICES 2020 within these vertical walls. So it highlights that these habitats could well be acting as biodiversity hotspot and can be shaped by multiple interactions. And this study also provides the first snapshot for future temporal monitoring, because we know that climate change is affecting and changing the water quality properties along the vertical axis. So these vertical wall sections are ideal sampling units to track these climate change impacts along the vertical axis. And the other important finding from this study is that we should prioritize more localized and multifactorial habitat variabilities rather than focusing on more generalized approaches. Study also highlight that integrating, like having a multidisciplinary approach when investigating these along these vertical wall communities, because having more diverse variables such as terrain characterizations, advanced oceanographic modeling, or our connected studies will be able to better explain the variability of the dataset. And for conclusion, this study provided the first detailed characterization of extensive megafaunal communities inhabiting this vertical wall habitat of the Galapagos Island. And the level of diversity was remarkable with 123 morpho species, and estimation-wise, this is an average of one new species observed for every 10 square meters, which is remarkable. Also, variability in the community structure could only be partially explained by site depth and by the primary abiotic factors that I used for this study. And species turnover was typically tenfold higher than the species nestedness, also highlight the potential of new species discoveries within these vertical wall communities. And finally, like having keystone structures, hyperlocal habitats, and VME indicator species also highlight the conservation priorities and possible gaps within this marine protected area. So, this study was also recognized by the International Coral Reef Society, and I received the graduation research fellowship for this work. And many thanks for my amazing supervisors for supporting me on this journey and providing me valuable insight to complete my master thesis successfully. So, these are some of the key references I couldn't list on the presentation, and thank you very much for listening.
For the last 13 minutes and 30 seconds, so pretty much on the time. I just wanted to, before we start the discussion, I just want to say really enjoyed it. what you did, and the picture you show us of the annotated image is actually quite impressive, and you can imagine the amount of work just to get to your data set, and then that couldn't stop it, so that's very nice. So I'm going to go to Julie for the discussion.
Do you know if this project continues or what would be the system?
Yeah, so actually in this project I had two components. Originally I was gonna investigate the acoustic data as well, just to create the terrain characteristics. So unfortunately the software I used for this study, it was QPS Chimera, and it was giving us so many issues, and we also contacted them. So that component is left from this study. So the next step is going to be getting those terrain characteristics, which will enable us to like have a more insight about this data set and incorporate these terrain characteristics. And this data set is a multi-institutional data set. So there are also like parallel studies going on. Like a set of research group is also investigating the taxonomic diversity. So in the end, everything will be like compiled together and will like have a more complete idea of these vertical wall habitats.
Curiosity, as you said, you have worked with the data, you have worked with a lot of different taxa. So what was the most difficult for you to identify?
Sorry, I couldn't hear the last part.
What was the most difficult taxa for you in order to identify?
So that's a good question, because in this analysis I left out poriferans, it means sponges. So sponges diversity was crazy along this vertical wall section, and if I annotated those things, I wouldn't have enough time to like annotate, because I already did 18,000 annotations, even with sponges. And if I left out some like sponges completely, and it dropped like 13,000. But I didn't annotated interesting sponges, only the structure forming. So can you imagine, like if I annotate all the interesting sponges, it will reach like 30,000 or something. So maybe the next step, one of the next steps would be like try to subsample and have like a sample methodology to incorporate sponges into this data set.
So thank you very much. Huge work.
Okay, thank you for your presentation. I have several questions. The first one, so you showed us a map of the Galapagos NPA with all the sampling sites. My first question was about the fundamental differences that you have among those sampling techniques. What are the differences beyond the depth?
Yeah, so it's also important because I had unbalanced sampling structure, because these are explorative dives. So we don't know whether we'll find a vertical wall or not. So once we find a vertical wall, you just sample. So like in some sites, I only have one vertical wall, and some sites I have 3 vertical walls. So it's not balanced at all, and the sampling effort is determined by the length of the vertical wall section. So in order to like counter this, that's why I investigated on sample completeness. It's a new approach by Joss, and I have the citation there listed. So they say that even though you have unbalanced sampling effort, you can still compare the species richness values across depth gradients if you calculate the sample completeness and if you have a complete sampling.
Yeah, I agree with that, but my question was more environmentally, what are the differences among those sites? I mean, I don't know if there are, for instance, different oceanographic zones, different data fields, or different currents, different nature of substrates, different slopes, or whatever. The kind of information that could have helped me, trying to understand what you were trying to compare. There's something that's always amazes me, is the level of communism in the deep sea ocean. It's not new. Just for the story, I was also attending the defense of Blake a few years ago. It was not here, but
so like Galapagos is like confined by 3 major oceanographic currents. So there might be some bias in this side, because there's like a major current coming through this section, and when you compare the salinity and temperature values, I also did the correlation, and it was revealed that temperature and salinity is collinear to depth. So I left out temperature and salinity in this case, but I mean I couldn't see any like contrasting effects based on those two variables, and I have only considered like temperature and salinity in this study.
You showed us some results for alpha diversity that kind of puzzled me, with values for Shannon and the Simpson diversity that I've basically never seen before. My neighbor is much more comfortable than me to speak about that. But, I thought that Simpson diversity was supposed to be composed between 0 and 1. Am I wrong? I'm wrong. There is something else happening here. So we go back to that. So maybe just the last question I didn't follow. You say that in the conclusion that the study highlights the need for conservation strategies.
Yeah.
Why?
So in Galapagos region, there are like coastal bioregions that they have already established, but they have never like gone into these deeper waters. And from my data set, as you have already seen, there are like keystone structures and a lot of like biodiversity hotspots within these vertical wall sections. So like there is still undiscovered biodiversity there, and like spatial management should then be like focused on these deep waters as well, rather than focusing only on the coastal management areas. And on the other hand, there's not much data, and this is like a very fresh data set from these vertical wall sections. So I think diversity-wise, it's imperative to like protect this existing biodiversity, because like 123 morpho species is like a very high amount of biodiversity just within these small vertical wall sections.
Maybe just the last very quick one. How do you take into account colonial species for your alpha diversity and disease calculation? Do you have solitary species and colonial species?
Yeah, so for colonial species, like let's say Madrepora aquilata,
Yeah.
so I mean, I use an approach where like one coral head is counted as one individual. I mean, it is like a very accepted method, also like applied in deep sea biology studies. So that's how like I incorporated colonial species and consider them as individual species.
This topic is pretty far from my background, so I'm not going into details of the presentation, but that's like more, in your opinion, which could improve the monitoring and in order to understand how this very important system reacts, which can be improvements in terms of instruments used to monitor the area, or approaches, different approaches, monitoring approaches to stand better there.
Yeah. Yeah. One way is like do predictive habitat modeling, because like if you can predict where these like similar communities can arise, so there's a possibility there can be other vertical wall sections within these Galapagos marine reserve. The main limitation is money, I would say, because this kind of research is very expensive. Like this research was funded by Schmidt Ocean Institute. Otherwise, like getting permits and like incorporating ROV is really money consuming. So maybe like multiple countries or multiple agencies can like come together and maybe explore more on this pristine habitat, because there's not much research in this area. So I would say maybe like do more research first, should be a first priority, and also like predictive habitat modeling just to see where these similar habitats can occur.
I have time this time, so I'm going to ask a question. While we're on this, you quantify sampling effort as a number of individuals.
Sorry?
You quantify the sampling effort in these graphs as the number of individuals that you allocated. Could you have taken another way of quantifying that effort as maybe?
Yeah, I mean, I could do this with area sampled instead of number of individual sampled. I tried to do that, but the code was not working for area sampled.
For area,
Yeah, cumulative area sampled rather than the cumulative number of individuals. And my supervisor said that for this thesis, it's okay to like go
What do you
with.
mean it was not working?
I mean, I couldn't make it happen with the code I had, like
Okay.
with the INX
Because
package.
it can give you a very different picture because now you're considering that one wall, one side is homogeneous. And I get a feeling just looking at the picture, you're sure that it's not the case. So you might get a different picture from that. Are these raw Shannon diversity and Simpson, or are these other, did you do something to those numbers here?
These are Hillinger transform
Yeah.
density values.
Do you use other information for this? I would not.
Oh no, sorry, not for this, not for this,
Okay.
sorry.
But are these exponentials?
Yeah, exponentials.
Just
Yeah,
like
exponentials.
okay.
Yeah,
So these are actually number of species.
Yeah, it's like raw-
That's why we're
raw values.
for these
Yeah.
values rather than the absolute bytes. Regarding the method of diversity analysis, I was just wondering why did you choose to use like turnover nestedness? With that, the nestedness is like very difficult to interpret sometimes. Because I don't know which one you use because there's different versions also. But you more commonly use the turnover richness difference partitioning because it's much more straightforward to interpret. Why did you use the? Is there a particular reason you choose the nestedness?
I mean, I was interested about like having a two sides comparison, and I thought that maybe like investigating on turnover and nestedness may give us more understanding about whether there's a species replacement or is it like having the same species set across different depths of sites. So that's why I choose this
The
one.
difficulty is that it's not always the one you use the additive one. There's one way to compute this is not additive, and that makes it very difficult. But I see you use the additive one, so that makes it fine. I don't see any questions from people following online. Do we have questions from the audience? We have time for one quick question. No? Then we'll just have to congratulate you on your
Thank you.
Next up is Caleb.
Thank you.
Yeah, we're just gonna wait for a minute so that people want to connect online to see if we will start from there, right?
Perfect, no worries.
Probably are there in advance if they want to, but just,
Yeah.
just make sure. So just wait a minute, I'll give you the. That's it. You ready to start, Kelly? So whenever you're ready, you can go ahead. You have 15 minutes to present your thesis.
Thank you. Okay, so yes, my name is Kaylin, and I will be presenting my thesis work where I focused on developing pressure dispersal methods within the SCARM framework. So the overarching theme of my thesis is that human uses of the marine environment it's a story of intensification and expansion, and we're seeing multiple different human activities and uses occurring within the same location and same area. So I believe as scientists, it's our job to understand where the different human activities are happening and how that this is affecting the different marine ecosystems, species. Yeah, so integrated ecosystem assessment is this cutting edge tool that provides this holistic perspective of all of the different human activities that are acting within an environment, and it's specifically designed to support and inform ecosystem-based management. So within integrated ecosystem assessments, there are 5 main stages where I just focused on the risk analysis stage. I think here it's very important to define some terms because these terms can be used, they mean different things in different disciplines. So I'll be referring to stressors, which are the different human activities and their subsequent pressures. So for example, if we're talking about shipping is an activity, and then the emission of underwater noise is an example of a pressure. And then I'll talk about receptors, which are the different ecosystem components. So depending on your interest, you can define this on the broad habitat scale or all the way down to the species level. And then when I talk about risk or impact risk, I'm talking about the likelihood of a change in a receptor for a given stressor-receptor interaction. So when we talk about impact chains, this is the link from an activity, its subsequent pressure, and a given ecosystem component. Then when we think about the combination of all of the possible activities within a given study site, all of their subsequent pressures, and all of the breakdown of the different ecosystem components that you're looking at, this combination is it's summarized within a linkage framework, which is at the basis of the SCARAM framework. So SCARAM stands for a Spatial Cumulative Assessment of Impact Risk, specifically designed to inform management. So when we talk about impact risk, this is calculated by the spatial distribution of stressors and receptors, or exposure, and the effect potential. So this is the relevant decrease in abundance of a given ecosystem component. Exposure is broken down into the spatial extent of an activity and how that activity's pressure disperses within the environment. And then when we talk about effect potential, this is calculated by both depletion and recovery rates, and even further, the hazard of a receptor for a given stressor, the magnitude of the stressor, the behavior, which is the likelihood of a stressor-receptor interaction, and the frequency of this interaction over a 1-year time period. So within SCARAM, since it's spatial, it works within this gridded system called C-squares, which is the standard system within the International Council for the Exploration of the Seas, or ICES. So for every impact chain that's present within a given area, impact risk is calculated along that impact chain and then aggregated within each specific grid cell within the study area that you're looking at. So if we're to focus specifically on exposure, when we're calculating the effect of an activity on an ecosystem component, if we exclude dispersal, we're simply looking at this area of overlap. And this is all that's considered in the effect on the ecosystem component. But when we incorporate the dispersal of the pressure from a given activity, it's increasing that area of overlap, and we're having a better understanding of how an activity is actually affecting spatially an ecosystem component. And so there are many different methods in how people have tried to quantify dispersal with several limitations. So some methods try to apply this uniform buffer around an activity, saying within 1 kilometer from the activity, you can see the dispersal of the pressure, but this is assuming a uniform effect across that buffer. Other methods try to incorporate this, a decay of effect over space and time with distance from the source, but this is not necessarily specific to a given pressure, and it also assumes equal spreading in all directions, when in reality, the dispersal of pressures can look something like this. So when we're assessing them with buffers and not specific methods, we're having both an under and overestimation of where the effects on an ecosystem are happening, and of course the magnitude of the effect. So within my study, I chose to focus on the dispersal of underwater noise because this is a very widespread and well-known pressure. It has been mapped with very sophisticated software in many different locations in different contexts, but the main problem with these mapping techniques is that they're not necessarily compatible to be integrated within any sort of impact assessment. So the objective of my thesis was, first of all, to map the dispersal of sound from different sources, and then apply my results, so my sound maps, within the context of the Scarum framework. So I focused on the Dutch part, or the westernmost part of the trilateral Wadden Sea. There is an ongoing Scarum project in this location. As well, it's an area of high importance because it is a UNESCO World Heritage Site and a Natura 2000 protection zone. So it's important that we understand where the human activities are happening and how we can better manage those. So the first part of my methods was to develop this simplistic source path receiver model where I identified the distribution of my source. So I chose to focus on continuous underwater noise from different ship types. So using vessel density information from EMODNet and the specific intensity of different ship types, I was able to create this source level map where I identified all of the grid cells within my study area that were considered sources and had sound emission coming from them. Then I created a transmission loss model, which basically calculates how sound propagates over space and time and how it loses its sound energy and intensity with distance from the source. So I applied a cylindrical spreading model where R is the distance between the source and a given receiver grid cell. So then I calculated what I'll refer to as received level maps, which are the sound maps. So as I said, I identified all of the source grid cells. I calculated the path between a source and a receiver grid cell, and I calculated the transmission loss of sound along that path. And then if we were to put ourselves in the perspective of a given receiver grid cell, I then calculated the cumulative received level from all of the possible source cells within the studied area. So then the second part of my methods was to find a way to incorporate this into the existing Scarum framework. So I chose to focus on hearing threshold shifts in different ecosystem components as a proxy for population decline. So threshold shifts is basically a decrease in hearing ability that persists either temporarily or permanently. And so I chose to implement this in two different ways because the methods that you pick to incorporate your spatial information within Scarum really matters. So I chose to try out two different ways of doing this. So the first way was to update how magnitude is categorized currently in the Scarum framework. So when there's no spatial or quantitative information about the magnitude of a stressor, it's assessed categorically from very low to maximum magnitude. So what I did with my receive level map, since I had a receive level value in every single grid cell in my study area, if the receive level was less than the ecosystem component's temporary threshold shift, magnitude was then categorized as very low. If it was in between the temporary and permanent, then magnitude is classified as medium. And then if the receive level was greater than the permanent threshold shifts, then magnitude is classified as maximum. Then the second method that I chose to do was to replace this hazard magnitude behavior term with a new, more biologically relevant scaling function. So similarly to magnitude classification, if the received level was below the temporary threshold and above the permanent threshold, then the scaling term was very low and very high respectively, but it was this in-between values that were logistically scaled to represent this more smooth transition of population decline with respect to the given received level. So the first part of my results is just my sound map. So I identified 6 different ship types that were available on EMODNet and also were present within the Wadden Sea linkage framework. So if we were to look a little bit closely just at one, this is for passenger vessels. We can see it's a little hard to see, but the western side of the Wadden Sea had a little higher received level noise levels, and the eastern part had lower levels. You can also kind of see some pathways of ship traffic and potentially some important ports. And so the implication of this is that I thought it was really interesting that the hotspots of noise aligned with hotspots of ship traffic, which in the Wadden Sea, it's highly dependent on the tidal action and how the tides are where ships can pass. I also thought it was interesting that across the entire Wadden Sea, the there were very few received level cells that were below or at the ambient underwater noise level, which is not in line with the Marine Strategy Framework Directive and these sustainability targets, which could indicate that there are these more chronic habitat level effects that are happening within the Wadden Sea. So for the second part of my results, I picked broadly 3 ecosystem components: cephalopods, fish, and marine mammals. And I identified the threshold shift limits based on a literature review. I found that cephalopods and fish had relatively similar threshold shift limits, and marine mammals had higher threshold shift limits unanimously amongst the literature. Then in comparison, so for the threshold shift limits with respect to the received level of sound, there were no received levels that were higher than the permanent threshold shifts for any ecosystem component, which I think is really awesome. For marine mammals, there were only a couple grid cells that were in between the temporary and permanent threshold shifts. So then here, this is the distribution of impact risk across my study area once I applied the cumulative impact risk calculations. So it's very hard to see any differences here, but based on a comparison between the cumulative impact risk from the baseline scenario, the categorical scoring method showed a 1% decrease in the total cumulative impact risk, and the continuous scaling method showed about a 2% increase from the baseline scenario. And then I think it's very important to compare my methods, because the way that we choose to, or the choices that I made to incorporate my received level maps into SCARAM, there was a 3% difference between the scenarios. So this can become really impactful when we're informing management and we're making decisions about, right now I'm talking about the broad ecosystem level, but then if we look even closer at the different ecosystem components that I assessed, the difference between even just the baseline and the second method is about a 5% increase in impact risk on marine mammals, which are very vulnerable, and we have to pay attention to this. And finally, if we are to break down the proportional contribution of different pressures, I thought it was very interesting that we can see how continuous underwater noise changes its ranks based on how it's incorporated into the SCARAM framework. So the first method showed that it decreased by 3 ranks, and the first method showed that continuous noise contributed 1 more rank than the baseline. So I just want to say that I think the main takeaway from this is that this method worked. So the method of mapping the dispersal of sound within this gridded system that was then compatible within the SCARAM impact assessment, now we have a better informed model that we can present to managers so that then they can make even better and even more informed decisions about the environment that they're currently managing. I think that it's important to note that this method can then be applied in other procedures. So we're already mapping the dispersal of contaminants from anti-fouling paint and pollution from ship discharges, and also the spread of invasive species. So since we're already mapping this distribution, if we're making these maps compatible with impact assessment methods, then it's possible to integrate dispersal of all of these different pressures, as many as possible, within integrated ecosystem assessments. I also think it's important to try this in other locations. They have applied the SCARAM framework in the North Sea, but in other locations, I made some very specific choices based on the Dutch Wadden Sea's environment. So it would be important to see what would happen if I changed the location, and also then to ground truth the results. So going out and measuring the received level of underwater sound at different locations to make sure that what I have measured or what I've estimated is actually representative of what's happening in the environment. Yeah, so thank you so much.
Thank you very much, Kevin, for this very interesting presentation. Excellent use of your time.
Thank you.
Good on that. Again, start the discussion. Go ahead, Estelle. All right.
Well, first of all, congratulations for the work. It was easy to follow the presentation. In that way is something nice. In fact, it is temperature more natural. And well, just to use this in order to discuss it a little bit. What would be the weak points of your method? Because you say that the strengths, but not about the weaknesses.
What would be the what point, sorry?
The weak points of your method.
The weak points? Yes. So because I was trying to map sound in this gridded system, there was a lot of detail that was lacking, as opposed to if I used a sophisticated just mapping technique specific for underwater noise. So I only really included this cylindrical spreading model, so sound can spread first in a spherical way and then in a cylindrical way. This is very basic, so I think that if we are able to find a way to have more sophisticated modeling, I chose to do all of this in R because that's how SCARM is calculated. So that was another challenge that I was trying to overcome, is how do I include the most amount of information and have the best model while keeping it in this gridded system and doing it in R. So I think if there's a way to have this more sophisticated modeling software in collaboration with R, I think that would be really nice. Yeah.
Well, you comment a little on the study area. So my question is, well, in that study area will be several stressors for the environment. So you will have to do a ranking of the stressors. In which position you will put the
Like if I was to rank them? Yeah. Well, even I was able to like calculate them, or do you want my opinion on?
Yeah, your opinion about, well, you are like an expert in underwater knowledge and about the study area, so in a ranking, which position?
Well, I think just in general, I think it's very impactful because it is raising the ambient noise level. So even though I found that it wasn't causing like permanent hearing damage or even temporary hearing damage, I still think that it could be having other effects. So I think in my study, I found that maybe it's ranking a little bit, like I would say it ranks lower than other pressures that are in the environment right now. But I also didn't really assess the other possible effects besides hearing damage. So I think that if I was to take that into consideration, maybe I would rank it a little higher, but based on the data, it's ranking pretty high in my opinion. Yeah.
Behind
Sorry?
On the top 3, which one will be the stressors?
Like what stressors cause underwater noise the most? Well, I guess you have to think about the different types of underwater noise as well. So since I just focused on continuous underwater noise, there's also underwater noise that comes from like actually scraping the bottom if you're dredging. I just like focused on the passing of a ship. But then impulsive noise, for example, was the most impactful pressure. This is like, you can use this from like sonar. Pile driving doesn't happen in the Wadden Sea, but that is typically the most impactful source of noise, but that was out of the scope of my study.
Thank you very much.
Thank you. Thanks.
Interesting, this last part of your answer, because you know that there are some investigation tools such as airgun that can be very, very impactful.
Yeah.
Can be, for instance, this approach used to estimate the impact of giving information to the policymaker.
Exactly, yeah. And so this is an impulsive type of sound, so I just wanted to focus on continuous to start. But I think, I believe that then the way that I calculate the transmission loss along the path is different for impulsive sound, so then that would have to be updated. But I would be really interested to see, because it has a way higher effect on marine animals and compared to continuous noise. But yeah, air guns, pile driving, like all of these, they're very impactful.
Because, for instance, I'm familiar with the Rock Sea and where it is the largest magnetic area of the world. And strangely, there are some activities such as seismic measurement are allowed. For instance, in the Mediterranean Sea, they are not allowed. So, do you think that your method can be easily transferred to different areas, such as polar winter?
Yeah, I believe so, and I think that was one of the main goals of my thesis, is to make this method, you know, you can't just jump to the end. You have to kind of, it's a stepping stone of you make a simple model. So I think this simple method is enough to then be applied to other pressures in other locations. When I talk about like the location-specific choices that I made about my transmission loss model that had to deal with like the depth of the Wadden and the tidal action and the frequency of sound that comes from ships, if it was high frequency, we would have to change the calculations a bit, but that is very minor in the scope of this sort of mapping technique that was used here. So I like to think that this can be applied, maybe not easily, but with a bit of time to a bunch of other different pressures, and yeah, hopefully impulsive sound, because it is the highest, like, it's the highest ranking pressure here. Yeah.
Last question. Sound propagation is affected by the distribution equation. Does your model take into account these changes in the model carbon characteristics?
No, it does not. Yeah, so at first when I first started reading about this, I thought that I should include like the absorption of sound just generally, but because it's low frequency, it's irrelevant. The absorption is like 0.001 across the whole study area. So that's why I say, like, if we did this in another location with a different source characteristics, then we would have to include this absorption term. There's also, you know, the reflectivity from sea surface roughness and sediment type. I think all of that would be done with more sophisticated modeling. But yeah, I think that is like next steps, and this is just laying a base for how can we incorporate the spatial information. Yeah. Yeah, thank you.
Yeah, sure. Thank you. Congratulations for your presentation.
Thank you.
I really like this idea of switching from a circular buffer zone for the dispersion of pressure to something that is more realistic.
Yeah.
But then you're using a case study with sound, for which dispersal law is pretty much ends up in a circular dispersion zone. I was like, okay, so you chose a perfectly valid pressure with sound, but maybe it was the easiest to
potentially, yeah. I think that, so, yeah, in other studies, when they do apply these buffers, so they'll say like, okay, we have a cruise ship port right here, and we have a coral reef here along this, you know, coastline. We can see an effect on the coral within 1 kilometer, therefore you put your 1 kilometer circular buffer around that. So maybe it does disperse in a, like, it radiates out in the same sort of fashion, but we're not necessarily calculating how the pressure is dissipating as well. So the spatial dispersion can follow the same sort of trajectory, but it's also this, like, the effect of that over space and time is what's different as well. So we're not just assuming this buffer, it's kind of taking everything into account, yeah.
You mentioned in your conclusion that you would like to maybe address 3 other pressures with contaminants and invasive species. Why the 3? And why data would you need? That's completely different, I guess, to model the pressure dispersion for the 3
Yeah, okay, so I picked these ones just as an example. So I was looking at, you know, which other pressures have been mapped extensively, similar to sound. So yeah, that's why I picked these 3, just as an example, because there's a lot of information on how they spread in the environment. I don't think that I know the specifics of how these are dispersing, but based on how I did my study, you first have to understand the physical oceanographic parameters that are affecting how these pressures are moving and interact with the environment. So that's the first step of any of these. And because there's so much information on that already, and people have already been mapping this, I think that it's just a matter of accessing and compiling the information and then applying it within this same gridded system. Yeah.
Okay, maybe just a last question. I was wondering about the temporal dynamics of the pressure. You have some current pressures, and like when the boats comes by, it just comes and makes noise, and then it's gone.
Yeah.
And
Sound is gone, so
Yeah.
up to you.
Yeah, that is very tricky because, yeah, first of all, with the data that I was working with, on a ModeNet, vessel density is measured in like hours per square kilometer per month per year. So it's very, in my opinion, it's a little strange. So I converted this into the instantaneous number of ships for a grid, within a grid cell over a 1 year, like average over a 1 year time period. So within each grid cell, it would be something like 4 or 2.1, like it's not exact and it doesn't really take into this movement parameter. So that is definitely something that is valuable information to provide, but was, I think, definitely a couple steps above what I was looking to do. Yeah.
Okay, thank you very much. And congratulations.
Thank you.
Thank you very much, Caleb. Any questions from the audience? Yes.
Yes, I have a question about the cylindrical dispersion of sound.
Mm-hmm.
Is the distance or the speed or the loss of sound energy affected, for example, by that depth of the water pool?
Yes. Yeah, so when you look at the dispersal of sound and how sound propagates in the ocean, from its source at the surface, it's, actually I'm gonna show this, it propagates initially in a spherical manner. In the same sort of calculation, it's like 20 log r with the distance from the source. And then it proceeds to propagate in a cylindrical way. So that's kind of the physical propagation modeling, but because it was in the Wadden Sea and the tides changed so much and it's generally very shallow, I chose to just exclude the spherical method and only apply the cylindrical method because it's so variable and shallow. And then with respect to the speed of sound, so the absorption coefficient considers, speed, temperature, salinity, depth, all of that stuff, but because absorption is frequency dependent, I was using a low frequency source, which made my absorption term insignificant. It was very low. So I excluded that as well. But if it was with a high frequency sound, it would definitely be relevant. You can see that the transmission loss a lot greater over space and time. Yeah. Yeah.
All right. Thank you very much. Congratulations and congratulations to all.